Hello, a very good evening everyone. Just confirm me whether my voice is audible or not. Just confirm it once. Everyone, just confirm it once whether my voice is audible or not. Audio video clear? Okay, so I welcome you all to the IMS GATE Academy YouTube channel. We are running with this most expected concept series for GATE-24, and I am here to discuss about the most important concepts for environmental engineering. For all the civil engineering students, it is one of the very important subject, one of the highly weighted subject. If you appear for civil engineering as a core subject, the weightage of environmental engineering is like 12 to 15 marks, one of the highest for civil engineering students. On the other hand, if you separately appear for environmental engineering as a second subject, the weightage of the topics will going to increase, right? When you see the syllabus of environmental engineering, all these topics have comparatively more weightage. So one single preparation is helping you for 2 examinations. If you are preparing for other technical exams apart from GATE, again, this is one of the very important topic. So today we will going to see about the extraction of groundwater. My dear students, this is a topic which is common for environmental engineering, hydrology, and also some part of it is common with geotechnical engineering. So again, this topic is very important, one of the easiest topic. From this topic, multiple select question can be framed. N number of multiple select questions can be framed. So our session for today will be focusing on how to appear for this multiple select question by knowing all the facts regarding this topic, and also if any numerical comes from this topic, how to deal with that. Okay, so we'll start with the extraction of groundwater. If I talk about the entire environmental engineering, so environmental engineering is broadly classified into raw water engineering, wastewater engineering, then air pollution and solid waste management. Precisely if I talk about raw water engineering, the first part of raw water engineering is calculating the total quantity of water which is required in the community, which comes under the topic of water demand. Once you know the total quantity of water required in the community, the next step is to identify different sources of water from where this water can be extracted in order to supply it to the community, right? So our topic of discussion is sources of water. These sources of water are broadly classified into surface sources like rivers, lakes, ponds, sea and ocean, or subsurface sources, that is the underground water. So today we will going to discuss each and every aspect, how we are extracting this underground water, what are the different parameters which affects the extraction of this underground water. And if any underground flow is happening below the earth's surface, what are the different factors which are affecting that flow? So we will start with this. The first topic of discussion is groundwater development. That is, if you move below the ground level, how the water is available in different layers, or precisely what are the different layers in which water may be present or not present. If water is present, in which form this water is present. Okay. So if this is my ground level, and I move below the ground level, there are different layers, right? On moving below the ground level, the layer of earth are broadly classified into 2 categories. Bottom layer is known as zone of rock flowage, right? You can just imagine this layer as a layer of very high pressure. Majority of the soil medium is present in the molten form, right? So this is the zone where most of the material is under the state of plastic stresses. The pressure is so high. And when you imagine this layer, one thing is clear, that whatever water will be present in this layer, that water is present inside the crystal structure of the medium particles, right? If I talk about this layer, so this is the layer of very high pressure, and that high pressure results into plastic stresses. Permanent deformations of the soil medium is happening. and water is present inside the crystal structure. Remember, in chemistry we have drawn some crystal structure like this. This is kind of crystal structure for any soil particle, and water will be present inside this crystal structure. This is my water which is present inside this crystal structure. So if I need to extract this water which is present inside the crystal structure of the medium particle, I need to break these bonds. I literally need to break the crystal structure in order to extract this water, right? Breaking of this bond requires huge amount of energy. And if we are supposed to extract this water by providing this much amount of energy, this may not prove to be feasible. It requires a lot of money, it requires a lot of energy, and extracting this underground water at this cost is not at all feasible. So with respect to the extraction of underground water, this layer is of no use. Zone of rock flowage is of no use, right? Because there are three reasons for it. First one is, this layer is under the state of plastic stresses. Due to plastic stresses or high pressure, water is present inside the crystal structure of the soil medium particles. In order to extract this water, this is the third reason. In order to extract this water, we need to break these bonds so that this water which is present inside the crystal structure may come out. And breaking of these bonds requires huge amount of energy, which is directly involved in the cost which is required to extract this water. So basically, with respect to the extraction of underground water, this zone of rock flowage is of no use. It is of no use. The depth of this zone of rock flowage may extends up to several kilometers. Okay. Now, above this layer, we have zone of rock fracture. Now, in this zone of rock fracture, the water is present between the voids of the soil medium. Water will be present in the voids of the soil medium like this. So, if this is my soil medium, water will be present inside the void of the soil medium. This is my water present. This is my water present inside the voids of the soil medium. That's why this is named as zone of rock fracture. Okay. In zone of rock flowage, water was present inside the crystal structure. In zone of rock fracture, water will be present in between voids of the soil medium. Now, the zone of rock fracture is further classified into two zones. First one is known as zone of saturation and the other one is known as zone of aeration. This zone of saturation is also known as groundwater table zone. In this zone of saturation, groundwater table will be present. The upper layer of the zone of saturation is marked by the upper layer of groundwater table. Wherever your groundwater table ends, your zone of saturation also ends. This zone is completely saturated. This zone is completely saturated and water is present inside the void of the soil medium. So, extraction of this water comes to be very easy, right? Because this water is only under the state of hydrostatic pressure. This hydrostatic pressure can be very easily overcome by pumping out this groundwater, right? That much amount of energy we can supply to extract this underground water. So, when I talk about till now, there is only one layer which is known as zone of saturation, from where we can very easily extract this water, because in zone of saturation, water is only experiencing hydrostatic pressure. And to overcome this hydrostatic pressure, you will not require much amount of energy. And that much amount of energy can be supplied either by using pumps or by using tube wells. Okay. Submersible pumps you might have heard about, right? Those submersible pumps are basically used to extract this underground water. Now, above this zone, the zone of aeration is further divided into three layers. This one is known as capillary water zone. Above that you have intermediate water zone, and above that you have the root zone. This capillary water zone is completely saturated by capillary action. This capillary water zone is completely saturated by capillary action. But we know that when water undergoes capillary action or capillary rise, this water is experiencing surface tension. Okay. Now, in order to extract this water from the capillary zone, you need to overcome this capillary tension, which again requires extra amount of energy. And if you need to supply extra amount of energy, you need to involve some extra amount of cost. So, extracting this water from capillary zone again does not become feasible, because due to added capillary tension, you need to supply extra amount of energy. In this zone of saturation, water is only under the action of hydrostatic pressure. But in this zone of capillary water zone, water is under the added effect of capillary tension. In order to overcome this capillary tension, you need to supply extra amount of energy, which makes this zone not at all feasible for the extraction of groundwater. Above this, you have intermediate water zone. The degree of saturation for this intermediate water zone is less than 1. Since the degree of saturation for this intermediate zone is less than 1, again extraction of water from this zone is again not feasible. Above that, you have the root zone. This root zone is completely saturated during the time of irrigation. Whenever you are just flooding your fields in order to irrigate your field, that is a time when this root zone will be completely saturated. But apart from that, majority part of the year, this zone does not contain sufficient quantity of water. The degree of saturation is supposed to be less than 1. Okay. So, this zone again does not becomes a feasible area from where underground water can be extracted. So, if you move down below the ground level, there is only one layer which is known as groundwater zone or zone of saturation, from where you can extract the underground water very feasibly. Okay. So, when I talk about the extraction of groundwater, all the extraction of groundwater will be done through this groundwater zone. Okay. So, I have written few details about this. So, when I talk about zone of rock flowage is a zone of high pressure. Medium particles are subjected to plastic stresses. Water is present inside the crystal structure of the medium particles. On the other hand, zone of rock fracture is a zone in which medium particles are subjected to medium pressure, that is less pressure. Medium particles are subjected to elastic stresses, and water is present inside the voids of the medium particles. So, there is a possibility in the examination that it can be asked that water is present whether inside the crystal structure or inside the voids of the soil medium. So, you need to keep a check in which zone water is present where. So, only in zone of rock flowage, water is present inside the crystal structure. Remaining in all the layers, water is present inside the voids. Okay. One more possibility of question can be, so out of all the zones, which zones are completely saturated? Which zones are completely saturated? Again, a multiple select question can be framed from this, right? You may be given different layers and you may be asked which zones are completely saturated. So, for this, answer is first layer which is completely saturated is known as zone of saturation. Zone of saturation, which is also known as groundwater table zone. or groundwater zone. The second layer which is completely saturated is capillary water zone. Capillary water zone. Okay. So this is the first variety of multiple select question that can be framed. So you need to keep a check on these two layers. Again, from this topic, one more question can be framed, and that question can be why extraction of groundwater is not feasible from capillary water zone. From capillary water zone. From capillary water zone, right? Now for this, the answer being, if you look into the capillary water zone, this is my capillary water zone, and below this I have zone of saturation. So this is my zone of saturation, ZOS, and this is capillary water zone. This is capillary water zone. Now this capillary water zone is completely saturated due to this capillary action like this, right? It is completely saturated due to this capillary action. If you plot the pressure which is felt by this water which is present inside the void, it can be marked like this. I'll start with zone of saturation. For zone of saturation, it will be under the state of hydrostatic pressure, this only. This is zone of saturation. It is under the state of hydrostatic pressure like this. It is only experiencing hydrostatic pressure like this. This is the hydrostatic pressure which is experienced by water which is present in the zone of saturation. So this is my hydrostatic pressure. And when you look into the same water which is present in the capillary water zone, this water is under the state of capillary tension like this. This water is under the state of capillary tension like this, right? This is your capillary tension. When you look into this water which is under the state of hydrostatic pressure, if you consider two layers of water, this is the lower layer of water and this is the upper layer of water. This upper layer of water is trying to compress the lower layer like this. It is trying to compress the lower layer, right? This is how the hydrostatic pressure is created. On the other hand, if you look into this capillary tension, so this is my lower layer of water which is present in the capillary water zone, and this is my upper layer of water which is present in the capillary water zone, right? This upper layer is trying to pull this lower layer. This upper layer of water is trying to pull this lower layer, right? You can either understand this in the form of layers or even you can understand in the form of zone. This upper molecule of water is trying to pull the lower molecule of water, due to which capillary tension is produced in the capillary water zone. So if we need to extract this water, we need to overcome this capillary tension. In order to overcome capillary tension, we need to supply extra amount of energy. And whenever extra amount of energy is supplied, it comes with added cost. And we need not to provide that added cost in order to extract this underground water. So this capillary water zone is not a feasible source of extraction of underground water. Reason being, extra amount of energy is required to overcome this capillary tension. And that extra amount of energy will involve extra amount of cost. That's why water is not extracted from this capillary water zone. Inside the ground level, there is only one zone from where underground water can be extracted, and which is through zone of saturation or the groundwater table zone. So wherever groundwater table is present, we will going to extract the underground water from that zone itself. Okay. So these are the different layers if you move inside the ground level, where water can be present in different forms. So you have root zone, intermediate water zone, then capillary water zone, then groundwater table zone, and below that you have zone of rock flowage. Okay. So this is about your groundwater table. Now moving on with this, once you know that you need to extract groundwater as a source of water in order to supply to the community. As an engineer, you need to find out whether sufficient quantity of water is present in this ground area or not. Second question is whether the extraction of that groundwater is feasible or not, right? So this extraction of groundwater depends upon the two parameters. First one is known as the porosity. No doubt you have learnt about the definition of porosity as defined as volume of voids divided by volume of soil medium. I would like to add one more thing. For example, this is my soil medium like this. This is my soil medium. And these are the soil particles. Okay. So porosity basically tells us about how much amount of voids are present in the soil medium. So this is the voids present in the soil medium. These are the voids which are present inside the soil medium. And water that we are talking about for extraction, that water will be present in these voids only. Water will be present in these voids only. These are the voids of the soil medium. These are the voids of the soil medium. Water will be present inside these voids. So water will be present inside these voids. So I think you are getting an idea. And that idea is, if more voids are present, more quantity of water is stored in that soil medium. If more voids are present, then soil medium can store more water. Soil medium can store more water. So basically here comes the relation between porosity and the extraction of groundwater. As an engineer, if we are visiting any site from where water has to be extracted, first we need to check whether sufficient quantity of water is stored inside that soil medium or not. And that is checked using the parameter which is known as porosity. So basically we do this underground exploration. We take out the soil, underground soil, and we check the porosity of this soil. If this porosity of soil is sufficient, then we say that sufficient quantity of water is stored inside the soil. Because if porosity of the soil is more number of voids are present. And if more number of voids are present, it means that more amount of water is stored inside the soil medium. So first of all, let me define porosity. Porosity in is equal to volume of voids divided by total volume of soil medium. So this is volume of voids divided by total volume of soil medium. Total volume of soil medium. More the number of voids, more voids, or I'll start like this. More the porosity, it means more voids. And if more voids are there, more water can be stored. More water can be stored. So porosity basically tells us what is the water storage capacity of the soil medium. More is the number of voids, more will be the water storage capacity. Okay, now from here a question comes, and that question is, which soil can store more water? Coarse grained soil or fine grained soil? Again, one of the favorite statement for GATE. Which soil can store more quantity of water? Which soil can store more quantity of water? Two examples are there. Coarse grained soil and then you have fine grained soil. Which soil can store more amount of water, right? So here student usually make a common mistake, and that mistake we will discuss. Okay. Now when you look into the coarse grained soil, you can imagine that we are talking about larger size of particles. And when we are talking about fine grained soil, we are talking about smaller size of particle. So student directly relate the volume of voids with the size of the particle. Okay. And that is one of the most common mistake any student does. Now just you observe this coarse grained soil. For this coarse grained soil, this is my coarse grained soil. I am making larger size of particles like this. This is my coarse grained soil. When I talk about fine grained soil, I am talking about smaller size of particle like this. I am talking about smaller size of particle like this. Now you need to compare the volume of voids. Whichever soil has more volume of voids, that soil can store more amount of water. Okay. When you look into the coarse grained soil, for coarse grained soil, size of volume of one void or volume of one void for coarse grained soil is more. Volume of one void is more for coarse grained soil, right? On the other hand, when you look into this fine grained soil, this is the volume of void. This is the volume of one void. And it is clearly visible that for fine grained soil, volume of one void is less. Volume of one void is less. Now just by observing this, student makes his or her conclusion that coarse grained soil can store more amount of water. No, my dear. When I talk about volume of voids is volume of one void multiplied by the number of voids. So volume of void is volume of one void multiplied by the number of voids, n. Okay. When you look into the coarse grained soil, number of voids is less. Number of voids is less. I'll name this as n coarse grained soil. On the other hand, number of voids for fine grained soil are very high. Number of voids are more. Number of voids are more. So this is number of voids for fine grained soil. When you compare the number of coarse grained soil and fine grained soil, number of voids of coarse grained soil, this is very, very less than number of voids for fine grained soil. So when you take this as a single parameter, volume of one void multiplied by the number of voids. So this is volume of one void for coarse grained soil multiplied by number of voids for coarse grained soil. This factor comes out to be very, very less than volume of one void for fine grained soil multiplied by number of voids for fine grained soil. And the reason being, volume of one void for fine grained soil is less, but the number of voids which are present in fine grained soil, they are huge, very high in number. So this quantity comes out to be more as compared to coarse grained soil. So volume of voids for fine grained soil is comparatively more than the coarse grained soil, due to which water storage capacity for fine grained soil is more than the coarse grained soil. Okay, so do not make this mistake. Whenever we are talking about volume of voids, we are talking about two things: volume of one void and number of voids. And you need to study these two simultaneously in order to calculate the total number of voids which are present in the soil medium. Okay. So for this question, which soil can store more quantity of water? So fine grained soil can store more quantity of water. On the other hand, we can also say that porosity for fine grained soil is more as compared to the coarse grained soil. So I hope you have understood this. So this is the first factor, porosity, which helps us decide how much quantity of water is stored in the soil medium. If the porosity of the soil medium is more, it can store more amount of water. So basically, if you need to check the storage of water inside the soil medium, we will check the parameter which is known as porosity. Now comes the second parameter, which decides how easily we can extract this stored water. And that parameter is known as permeability. So permeability basically tells us how easy it is to extract this stored water. Okay. Permeability is defined as the ease with which water can flow through the interconnecting voids of the soil medium. This is how we define the permeability. Now you need to understand what does permeability exactly tells us about. Okay. For that, again, I need to draw a soil medium. So this is my soil medium. Like this. And water is flowing through the interconnecting voids of the soil medium like this. This is the flow of water which is taking place through the interconnecting voids of the soil medium. permeability is simply defined as the ease with which water can flow inside the soil medium. Now just observe this more carefully, what we mean by that. When the water is flowing inside the soil medium, this surface of the soil medium, this surface of the soil medium is applying the frictional force over the flow of this water, right? When the water is flowing through the interconnecting void, this surface of the soil medium is applying the frictional force over this flowing water. This surface of the soil medium is applying the frictional force over this flowing water. This surface of the soil medium is applying the frictional force over this water, like this. So this surface of the soil medium is applying the frictional force, or it is creating hindrance for this water to flow through the interconnecting voids. If the friction applied by the surface of the soil medium over this water is less, it means water can easily flow inside the soil medium. It means permeability of the soil medium is more. What I said just now, if frictional force applied by surface of soil medium is less, if the frictional force applied by the surface of the soil medium is less. I am highlighting this. Frictional force less. If the frictional force applied by the surface of the soil medium is less, it means water can flow easily. Water can flow easily through the interconnecting voids. And if water is flowing easily through the interconnecting voids, it means that permeability of the soil medium is more. It means that permeability of soil medium is more. Permeability of the soil medium is more, right? More the frictional force, more the hindrance. More the hindrance, more difficulty will be faced by water to flow through the interconnecting voids. And if more the hindrance is offered by the soil medium in the flow of water through its interconnecting void, less will be the permeability. On the other hand, if frictional force is less, water can easily flow through the soil medium and the permeability of the soil medium will be more. So basically, permeability is directly related with the frictional force which is applied by the surface of soil medium over the flowing fluid, right? Frictional force applied is less, so permeability will be more. If frictional force applied is more, the permeability will be less. Now this frictional force also depends on this surface area. More the surface area of the soil medium, more will be the frictional force that is applied over this flowing water. What I am saying is, more the surface area, more will be the frictional force, more will be the frictional force. More the surface area, more will be the frictional force that is applied by the soil medium over the flowing fluid. And if more frictional force is acting, obviously permeability of the soil medium will be less. Now again comes a question. Which soil allows easy flow of water through its interconnecting voids. Easy flow of water through its interconnecting voids. Through its interconnecting voids. Again, one of the statement, right? All these are statements. This statement can be said like this. Which soil allows easy flow of water through its interconnecting voids? Coarse grained soil or fine grained soil? Like that. So again, coarse grained soil, and second you have fine grained soil. Next you have fine grained soil. So which soil allows easy flow of water through its interconnecting voids, whether it is coarse grained soil or fine grained soil? Now observe this. When I talk about the coarse grained soil, this is the size of the particle. This is the size of the particle like this. This is the size of particle. For fine grained soil, this is the size of particle. Okay. Now again the concept of total surface area. We need to see which soil has more total surface area. When I talk about a coarse grained soil, surface area of one particle is more. For coarse grained soil, surface area of one particle is more. Surface area of one particle is more. But number of particles for coarse grained soil, is less. And this we have just now seen. On the other hand, for fine grained soil, surface area of one particle is less. Surface area of one particle is less. It is less. But number of particle for fine grained soil, are more. Number of particle for fine grained soil are more, right, with compared to coarse grained soil. So again, when you need to calculate the total surface area of the soil medium, the total surface area of the soil medium is the product of surface area of one particle multiplied by the number of particles. So total surface area is surface area of one particle multiplied by number of particles. So these two quantities you need to keep a check while you are calculating the total surface area of the soil medium. So when you multiply these two quantities, surface area of one particle multiplied by the number of particles, the surface area, the total surface area for coarse grained soil comes out to be less than the total surface area of this fine grained soil. So total surface area of this coarse grained soil is equal to surface area of one particle for coarse grained soil. This is coarse grained soil multiplied number of particle for coarse grained soil. It comes out to be less than surface area of fine grained soil of one particle multiplied by the number of particles for fine-grained soil. Okay. Surface area of one particle for fine-grained soil multiplied by the number of particles for fine-grained soil. So when you observe these two quantity as a whole, the total surface area for coarse-grained soil comes out to be less than the fine-grained soil. And if the total surface area of coarse-grained soil is less, means coarse-grained soil offers less frictional force. It means that coarse-grained soil has more permeability. Coarse-grained soil allows easy flow of water through its interconnecting voids. I hope this analysis is pretty much clear to you. For talking about the ease with which water flowing inside the soil medium, we need to know about the surface area. If surface area of the soil medium is more, that soil medium will going to apply more frictional force over the flowing fluid, right? And if more frictional force is applied by the flowing fluid, it means that permeability of the soil medium will be less. But if the frictional force is less, then permeability of the soil medium will be more. So for soil which allows easy flow of water through its interconnecting voids is coarse-grained soil. Coarse-grained soil allows easy flow of water through its interconnecting voids. So whenever we are deciding on whether the extraction of this groundwater is feasible or not, we need to check on two parameters. First one is porosity, which tells us about how much quantity of water is stored inside the surface. And second is permeability, which tells us about how easily we can extract this underground water. So these two parameters should be checked when we are talking about extraction of the underground water. So this extraction of underground water basically depends upon two parameters, porosity and permeability. So this is the general way of representing porosity and permeability. Always remember two things. First one is porosity for fine-grained soil is more, means fine-grained soil can store more amount of water. Second, permeability for coarse-grained soil is more. It means that coarse-grained soil will allow easy flow of water through its interconnecting voids. Okay. Now coming to the definition part. So for porosity, we have already defined porosity is represented by N, which is volume of voids divided by total volume. This is my volume of voids. Volume of voids divided by total volume. Right. Similarly, permeability is defined using Darcy's law. Permeability is defined using Darcy's law. Permeability is defined using the Darcy's law. And through the Darcy's law, permeability is defined as the rate of flow per unit area, rate of flow per unit area per unit hydraulic gradient, per unit hydraulic gradient. So as per Darcy's law, permeability is defined as rate of flow per unit area per unit hydraulic gradient. Now we will see how we derive this. Okay. We will going to see the Darcy's experiment. For Darcy's experiment, there are certain assumptions. First assumption is flow is laminar. And second assumption is length of flow is approximately, length of flow is approximately taken equal to length of soil medium, is approximately taken equal to length of soil medium, is approximately taken equal to length of the soil medium, right? So these are the two assumptions when we talk about the Darcy's law. Now let us see what is the Darcy's experiment. So Darcy's experiment, is pretty much simple. We take this soil medium like this. This is my soil medium. This is my soil medium. The length of the soil medium is L. L is the length of the soil medium. Cross-sectional area of the soil medium is A. Right? This is the cross-sectional area of the soil medium A. This is my soil medium. I'll write this. This is my soil medium. Okay. Now, we allow the flow of fluid inside this soil medium. We allow the flow of water inside this soil medium. For that, we apply a head of water at the entry. The head of water which is available at the entry of the soil medium is H1. This is the head of water which is available at the entry. This is H1. Right. Under the hydrostatic head of H1 or the under the hydrostatic head of H1, we allow the flow of water through the soil medium. And when this water will flow through the soil medium, this water will flow through the interconnecting voids like this. And due to the frictional force applied by the soil medium over this water which is flowing through the interconnecting voids, this water will going to lose some amount of energy and some head loss will occur to this water. And when we collect this water from the exit end, the head available with the water is H2. The head available with the water is H2. This is the head of water which is available at the exit. This is H2. So at the entry, head of water available, head available with the water was H1. While flowing through the interconnecting voids, due to the frictional resistance offered by the soil medium, this water will lose some amount of energy and some head loss will occur, due to which at the exit the head available with the water is H2. Water is flowing through the interconnecting voids, and this, while traveling this length, the total head loss that occurred is, while traveling this length, so this is the head loss that occurred. This is H1 and this is H2. So this is my hydraulic gradient line, HGL. The total head loss is equal to, this is the total head loss. The total head loss that occurred is, this is the total head loss, delta H. The total head loss that occurred is H1 minus H2. Head loss is H1 minus H2, right? This is the total head loss. Now here I would like to define one more parameter which is known as hydraulic gradient. So hydraulic gradient I is defined as head loss per unit length of flow. hydraulic gradient I is defined as head loss occurring per unit length of flow. L dash is this length of flow. L dash is this length of flow through which water actually travels inside the soil medium. L dash is this length of flow through which water is actually traveling inside the soil medium. And here comes our first assumption, which says that the length of flow is approximately taken equal to the length of soil medium. The reason being, calculation of this length of flow is a very tedious task, right? Never ever we can approximately calculate this length of flow L dash. That's why this L dash is approximately taken equal to L. L dash is approximately taken equal to L because the error in L dash and L is slightly less, right? That's why this approximation can be done. So L dash is your length of flow. L dash is length of flow. L dash is length of flow and L is length of soil medium. L dash is the length of flow and L is the length of soil medium, right? Now, as per Darcy's law, discharge flowing through the soil medium is directly proportional to the cross-sectional area. The first thing is, as per Darcy's law, discharge flowing through the soil medium is directly proportional to the cross-sectional area. Second is, this discharge is also directly proportional to the hydraulic gradient I. More the head loss, more will be the length of, more will be the flow happening through the soil medium. So when you combine these two, Q is directly proportional to A and I. When you remove this proportionality sign, you will get one constant which is known as K I A. And this constant K is known as coefficient of permeability. This constant is known as coefficient of permeability. This K is known as coefficient of permeability, and here we will get one expression Q is equals to KIA. Now from here we define the coefficient of permeability. Just understand this, how we define. So this K can be written as K is equal to Q divided by I into A, right? If this I is equal to 1, means hydraulic gradient is 1. So this K is equal to Q by A. And this is what we call as rate of flow per unit area under unit hydraulic gradient. If I is 1, K is equals to Q by A. That is the rate of flow per unit cross-sectional area under unit hydraulic gradient. Okay. So this is the definition of your coefficient of permeability K. This is the definition of coefficient of permeability K using the Darcy's law. Now again with this relation Q is equals to KIA. If you take A this side, you will get Q by A is equal to K into I. So this Q by A is known as discharge velocity V, which is equal to K into I. V is known as the discharge velocity. V is known as discharge velocity. Now the question comes in your mind, sir, what is this discharge velocity? is that velocity through which water is flowing inside the soil medium? No, my dear students. This is not that velocity through which water is flowing inside the soil medium. Reason I tell you. When I talk about this discharge velocity is calculated using this complete area A. Using this complete area A, right? But tell me, whether the flow is happening through this complete area A? No. Flow is happening through the voids which are present in this area A. Flow is happening through the voids which are present in this area A. Flow is happening through these voids. Flow is happening through these voids which is present in this area A, and this is area of void, right? Water is not flowing through this entire area A. Water is flowing through this area which is available for the voids. Water is flowing through this area of voids, right? So this discharge velocity V is not that velocity through which water is flowing inside the soil medium. There is some other velocity that we will calculate just now through which water is flowing inside the soil medium. Okay. So this discharge velocity is calculated using A, and through the complete cross-sectional area A, flow is not taking place. Flow is taking place through this area of voids which is available. Now the actual velocity of flow is known as the seepage velocity. The actual velocity through which water is flowing inside the soil medium is termed as seepage velocity, denoted by Vs. So Vs is known as seepage velocity. It is known as seepage velocity. And what is seepage velocity? It is the actual velocity of flow. It is the actual velocity of flow. It is the actual velocity of flow. If water is flowing inside the soil medium, it will be flowing through this seepage velocity, right? Now, how to calculate the seepage velocity? So, by continuity equation, I can write, by continuity equation, I can write discharge Q is equals to A into V, where A is the complete cross-sectional area and V is the discharge velocity that is calculated using this complete area A, is equal to area of voids multiplied by the seepage velocity Vs. Multiplied by the seepage velocity Vs. Okay. V is the discharge velocity and Vs is the seepage velocity. Now just rearrange this. So you have V by Vs. I'll write like this. V by Vs is equal to area of voids divided by total area. Just multiply by the length of the soil medium, both in the numerator and denominator with this area, right? So this area of void multiplied by the length of soil medium will be the volume of voids. Similarly, this cross-sectional area multiplied by the length, this will be the volume of the soil medium. In this volume of void, water is present. So I can write this as volume of water. So this can be written as volume of water. So V by Vs is equal to volume of water divided by total volume of the soil medium. Okay. Now in the case of completely saturated soil medium, this volume of water can be written as volume of voids. Okay. But when the soil is not completely saturated, for that case we need to see. So we multiply and divide by volume of voids like this, and we just rearrange these terms. So V by Vs is equal to volume of water divided by volume of voids multiplied by volume of voids divided by total volume. Now this volume of water divided by volume of voids, this is known as degree of saturation S, and volume of voids divided by total volume is termed as porosity N. So V by Vs can be written as V by Vs can be written as N into S. Okay. From here, I can get the value of seepage velocity. Seepage velocity Vs is equal to V divided by N into S. This is my seepage velocity. And seepage velocity is that velocity through which water is actually flowing inside the soil medium, right? So, if you drop any particle, just observe this diagram. If you drop any particle at this end, and if I ask you when that particle will going to reach this end, for example, you dropped one drop of ink at this end, and I'll ask you in how much time that drop of ink along with water will reach this end. So, for calculating that time, the velocity that you will going to use will be the seepage velocity, Vs. So, basically this seepage velocity is used when we are calculating something related to inert tracer. Usually a question comes in the examination where you drop an inert tracer in well 1 and some details are given and you are asked in how much time that inert tracer will reach to well number 2. In that case, we will going to use the seepage velocity. Seepage velocity is the actual velocity of flow, and if the water is flowing inside the soil medium, it will flow through the seepage velocity, right? Okay, when you observe this expression for a completely saturated soil, when you observe this expression for a completely saturated soil, for completely saturated soil, for completely saturated soil, means degree of saturation is 1. So, seepage velocity is equal to discharge velocity divided by porosity. For a completely saturated soil, seepage velocity is equal to discharge velocity by porosity. Now, this porosity is always less than 1. Your denominator is always less than 1. So, the seepage velocity will always be more than the discharge velocity. If your denominator is always less than 1, then the seepage velocity will always be more than the discharge velocity. So, seepage velocity is always more than the discharge velocity. Your seepage velocity is always more than your discharge velocity, right? So, these two expressions help us in deciding through which velocity water will flow inside the soil medium. So, we know that by seepage velocity, water will flow inside the soil medium. Second, which velocity is more? When soil is completely saturated. So, when soil is completely saturated, your seepage velocity will always be more than the discharge velocity. Now, again one more question. What is discharge velocity? Discharge velocity is just an average velocity which is calculated by taking total area of cross section of the soil medium. It has no physical relevance. Seepage velocity has the physical relevance. Seepage velocity tells us by how much velocity water will flow inside the soil medium, okay? You can just note this down. Okay, moving on with this. So, this is again a very important topic which is common for environment, hydrology and even some part of it, especially the seepage velocity. This is common for geotechnical engineering, one of the favorite area for GATE exam. You will see questions from this area in every alternate year, right? Because there are 3 subjects attached to this topic, which is the extraction of groundwater. So now again I'll repeat myself. Extraction of groundwater depends upon 2 factors. First one is the porosity, which tells us about how much amount of water is stored inside the ground level. Second is the permeability, which tells us about how easily water can flow through the interconnecting voids of the soil medium. Okay. Now, moving on with this. So next topic of discussion is flow under gravity. So before beginning this topic, I'd like to ask you again something. If this is my soil medium, like this, and this is the groundwater table. This is my soil medium and this is my groundwater table, right? And water is flowing inside this. Water is flowing inside this under the action of gravity. Water is flowing inside the ground surface under the action of gravity. So whether all water will come out or all water will flow out from the soil medium, or some water will be retained over the soil medium. Now this we need to decide, whether all the water will flow out of the soil medium or some water will retain inside the soil medium. So this is the next topic of discussion. Flow is happening under the action of gravity. Okay. Flow is happening under the action of gravity. Flow is happening under the action of gravity. Okay. Now observe this very carefully. This soil medium contains particles like this. These are the soil medium particles. These are the soil medium particles like this, right? And flow is taking place through the interconnecting voids of the soil medium. Flow is taking place through the interconnecting voids of the soil medium like this. Flow is taking place through the interconnecting voids of the soil medium like this. Okay. Now observe this very carefully. When the flow is taking place through the interconnecting voids of the soil medium, there exists the adhesive force between water molecule and the molecules of soil medium. Due to this adhesive force, some water molecules are adsorbed over the soil medium. Some molecules of water are adsorbed over the soil medium like this. Some molecules of water will get adsorbed over the soil medium like this. Some water molecules will get adsorbed over the soil medium and they are retained against the action of gravity. Some water molecules are retained against the action of gravity. And which force is retaining these water molecules? The adhesive force between the water molecule and the molecule of soil medium. That adhesive force is retaining this water. So this is known as retained water. This is known as retained water, right? So when the flow is happening under the action of gravity inside the soil medium, some water will flow out. On the other hand, some water will still be retained inside the soil medium against the action of gravity due to the adhesive force between the water molecule and the soil medium. So if you just zoom this picture, this is my soil medium, this is my soil medium, and over the surface of the soil medium, these are the particles which get adsorbed like this. These are the particles which get adsorbed like this. These are the particles which get adsorbed like this, and this is known as retained water and it is also known as adsorbed water. This is also known as adsorbed water. And why this water is adsorbed? Due to the adhesion between water molecule and the surface of the soil medium. Due to the adhesion which is present between the water molecule and the surface of the soil medium. This is my soil medium. This is my soil medium like this. This is my soil medium. And this is my water molecule. And this is my force of adhesion, adhesive forces. This adhesive force will retain some amount of water inside the soil medium and will not allow all the water to flow out the soil medium under the action of gravity. Now, this phenomena is explained by two parameters. Quantity of water which is flowing out under the action of gravity is defined using the term which is known as specific yield. So, specific yield is defined as specific yield gamma S. Specific yield gamma S is defined as volume of water drained. Volume of water drained. Volume of water drained under the action of gravity divided by the total volume of medium drained. Divided by the total volume of medium drained. So, this is the volume of water drained under the action of gravity divided by the total volume of medium drained. So, this is Vd by V, where Vd is the volume of water drained under the action of gravity and V is the total volume of medium drained. Now, talking about this water which is retained against the action of gravity, this is explained by one parameter which is known as specific retention. Specific retention tells us about how much amount of water is retained against the action of gravity in the soil medium. So, this specific retention is defined as gamma R. This gamma R is equal to volume of water retained against gravity. Volume of water retained against gravity divided by the total volume of the medium drained. Divided by the total volume of medium drained. So, this is equal to volume of water retained against gravity divided by the total volume of medium drained, right? So, basically, if inside the soil medium flow is happening under the action of gravity, the amount of water which is draining out under the action of gravity is explained using specific yield, also known as specific capacity, storage coefficient or storativity. And the amount of water which is retained against the action of gravity, that is explained using specific retention. So, gamma S and gamma R, both the things are in front of you, okay. Now, let us see what is the relation between this gamma S and gamma R. Relation between gamma S and gamma R. Okay. Say this is my soil medium like this. This is my soil medium. This is my soil medium. And in between this soil medium, this is the void which is present. And water will be present inside this void. Water will be present inside this void like this. Water will be present inside this void. This is the water which is present inside the void like this. Okay. This is the void. This entire thing is a void, right? And water is present inside this void. Now, some amount of water will flow out, and for the same water, some amount of water will get absorbed over the surface like this. Some amount of water will get absorbed over the surface of the soil medium like this. Some amount of water will get absorbed over the surface of the soil medium. Some amount of water will get absorbed over the surface of the soil medium like this, right? Now, when we write gamma S is volume of water drained divided by the total volume of medium drained. Similarly, gamma R is equal to volume of water retained divided by the total volume of medium drained. When you add these two, so you have gamma S plus gamma R is equal to Vd by V plus Vr by V. This is equal to Vd plus Vr divided by V. Vd is volume of water which is draining out of the medium, and Vr is volume of water which is retained against the action of gravity. So, Vd plus Vr is the total volume of water which is present inside the soil medium. So, this Vd plus Vr is total volume of water which is present inside the soil medium. So, gamma S plus gamma R is equal to volume of water divided by the total volume. Now, just multiply and divide by the volume of voids like this, and rearrange this term. So, you have gamma S plus gamma R is equal to volume of water divided by volume of voids multiplied by volume of voids divided by the total volume. Now, again this volume of voids divided by volume of water, this is known as degree of saturation S, and volume of voids divided by the total volume, this is known as porosity N. So, one very important relation comes out, which is gamma S plus gamma R is equal to N into S. Mark it as very, very, very important, because we have seen many questions are framed using this expression. Gamma S plus gamma R is equal to N into S. Now, when we talk about this concept, there is one favorite question that was asked in GATE, and that is regarding change in groundwater storage. So, change in groundwater storage is nothing but volume of water which is draining out of the medium. So, if a question says calculate the change in groundwater storage, you simply have to calculate volume of water which is drained out of the soil medium. Okay. So, if any question related to that happens to you in the GATE examination, you are pretty much clear what to calculate. So, volume of water drained from the soil medium is also termed as change in groundwater storage. Okay. So, this is again a very important derivation regarding specific yield and specific retention. Okay. So, I hope all these things are clear to you. Moving to the last section, that is types of geological formations. Types of geological formation means whatever soil medium which is present inside the ground level, that soil medium can store sufficient amount of water, or whether the extraction of this water is easy or not. Okay. So we have different types of geological formation. The first type of geological formation is termed as aquifers. So aquifers are both porous and permeable. Aquifers are both porous and permeable. They are both porous and permeable, means they can store sufficient quantity of water. Even the extraction of this water from this aquifer is easy, right? So these aquifers are both porous and permeable. Next, if I talk about acutard, acutard are highly porous or they have high porosity. I'll write like this. Acutard have high porosity but water actually seeps through the interconnecting void. They are less permeable. They have high porosity but they are less permeable. They are less permeable. When I talk about this aquifer, water actually flows through the interconnecting voids. But in acutard, water actually seeps through the interconnecting void. The flow is not that much fluent. So water seeps through the interconnecting voids. Water seeps through the interconnecting voids. Through the interconnecting voids. Water seeps through the interconnecting voids, right? Similarly, for this aquifer, water actually flows through the interconnecting voids. Water flows through the interconnecting voids. Flows through the interconnecting voids. Water flows through the interconnecting voids. Now just observe these two things. First one is high porosity and here it is just porous. And second is permeable and less permeable. Remember, porosity and permeability we have also defined with respect to the size of the particle. As the size of the particle keeps on decreasing, if you decrease the size of the particle of the soil medium, permeability will also decrease and porosity will increase. So when you look into aquifer and acutard and you just think about the size of the soil medium particle, for aquifer, the size of the soil medium particle is comparatively more because it is more permeable as compared to acutard. So size of the particle for aquifer is comparatively more than that of acutard. Okay. Now next geological formation is termed as aquiclude. So aquiclude are highly porous. They are highly porous. They are highly porous but impermeable. But impermeable. They are highly porous but impermeable. So when you compare this aquiclude with acutard, so acutard was having high porosity, but they are somewhat permeable, right? On the other hand, this aquiclude is even more porous than acutard and it is not at all permeable. Water will face a lot of resistance while flowing through the interconnecting voids. Means the size of the particle present in this aquiclude is comparatively even less than that of acutard, right? So if I talk about size of particle, I'll write here size of particle, size of medium particle, Size of medium particle. So size of medium particle is highest for aquifer. Size of medium particle is highest for aquifer. Then it is for acutard. And last it is for acuclude. I just made the opposite signs. So aquifer has the highest size of the medium particle. Then you have acutard. And then you have acuclude. This is the order of size of the particle, right? And based on the size of the particle, we can also write down the relation between porosity and permeability of these geological formation. So if the size of the medium particle is like this, okay, if the size of the medium particle is like this, I can write the relation between porosity as, if the size of the medium particle for acuclude is least, means porosity for acuclude is the highest. Acuclude can store huge amount of water. So acuclude has the highest porosity. Acuclude has the highest porosity. Then we have acutard. And last we have aquifer. Right? Next one is the permeability. Permeability is directly related to the size of the particle. If size of the particle is more, permeability of the soil medium will be more. If the size of the particle is more, permeability of the soil medium will be more. So aquifer has the highest size of the particle, so permeability for aquifer will be the highest. So permeability for aquifer is the highest. Then you have acutard. And last you have acuclude. So this is the order for porosity and permeability for acuclude, acutard and aquifer. Okay. Last one is your acufuge. Now acufuge can be imagined in the form of rock beds, impermeable rock beds. For example, just imagine a granite rock like this. This granite rock will neither allow flow of fluid through its voids, it will not allow flow of fluid, neither any water can store inside this rock bed. So this acufuge is neither porous, they are neither porous nor permeable. They are neither porous nor permeable, means no water can store inside these acufuge and no water can flow through the voids of these acufuge. So in case of porosity and permeability, acufuge comes in the last. So acufuge comes in the last in both the cases. Acufuge comes at last. Acufuge has the least porosity and has the least permeability. Okay. Now this is one of the favorite statement that can be made in GATE exam. So please keep a check on this statement with respect to the porosity, order of porosity and permeability for different geological formations. Okay. Now moving on to the last thing, when I talk about these aquifers are further classified into three categories. These aquifers are further classified into three categories. First one is known as unconfined aquifer. Now all these classifications are basically done and many things can be just understood by looking into the names. first one is the unconfined aquifer. Now, if you imagine an aquifer like this is my ground level, this is my ground level, and this is my lower impermeable layer. This is my lower impermeable layer like this. This is my lower impermeable layer, right? Now, above this impermeable layer, if I have a groundwater table like this, and the upper level of saturation of the soil medium is marked by this groundwater table. This is the upper level of saturation. This is the layer which will be completely saturated. This upper level of saturation, if marked by the groundwater table, then it is known as unconfined aquifer. As the name says, unconfined. There will be no confining layer which will have the porous media which contains water, right? There is no confining layer. The upper layer of saturation for this medium is marked by this groundwater table. So when no confining layer is present, it is known as unconfined aquifer. This is my groundwater table and this is my ground level. When there is no confining layer, then it is known as unconfined aquifer. Water which is present inside the voids of the soil medium will only have hydrostatic pressure, will only experience hydrostatic pressure. Water present inside the soil medium, I am writing this. Only hydrostatic pressure. Only hydrostatic pressure. So basically, if you insert any piezometer, the head of water that is shown in the piezometer will be corresponding to this. This will be the head of water inside the piezometer. And this is known as the hydrostatic head. Okay. So water in unconfined aquifer is only experiencing hydrostatic pressure. The definition of unconfined aquifer is very simple. If there is no confining layer present for the porous media, it is known as unconfined aquifer. The upper level of saturation for this type of aquifer is marked by the groundwater table. Water present in this unconfined aquifer will only experience hydrostatic pressure. Now the next type of aquifer is known as confined aquifer. Now you can relate this. What do you understand by confined aquifer? So confined aquifer is basically that aquifer in which confining layers are present. So confined aquifers are basically those aquifers in which confining layers are present. So if this is my ground level, and below the ground level, if I have two confining impermeable layers like this, this is my first impermeable layer, and below this I have another impermeable layer like this. So basically two confining layers are present, and in between this confining layer, if you have a saturated soil mass like this, if water is present between the confining layers, so these two are the confining impermeable layers. So these two are impermeable confining layers. Impermeable confining layers. This one and this one. These two are impermeable confining layer, right? And if water is present in between this confining impermeable layer, it is known as confined aquifer. Now, water which is present in between this confining layer experiences two types of pressure. First one is the hydrostatic pressure, and apart from that, one more pressure is exerted over this water, which is known as artesian pressure. This water experiences hydrostatic pressure, hydrostatic pressure plus artesian pressure. Artesian pressure. This artesian pressure is basically due to the revolution of the earth about its axis. So when you just insert any piezometer inside this water, right? When you insert any piezometer inside this water, ideally the piezometer should show this level. Ideally the piezometer should show this level if this water experiences only hydrostatic pressure. But due to additional artesian pressure, the level or the head of water available with this is this much. This is the head of water which is available. And this additional pressure is known as artesian pressure. This additional pressure is known as artesian pressure. So water which is present inside the confined aquifer, it experiences two types of pressure. First one is the hydrostatic pressure, and apart from that, additional artesian pressure will be also acting over this water, right? So this is the second type of aquifer which is termed as confined aquifer. As the name says, confined aquifer means soil medium containing water is present between the confined layers, okay? The third type of aquifer is known as purged aquifer. The third type of aquifer is known as purged aquifer. The third type of aquifer is known as purged aquifer. Now understand this purged aquifer. This is my ground level. And below ground level, this is my groundwater table. This is my groundwater table, right? And below this, this is my impermeable layer. This is my ground level, this is my groundwater table, and below this you have the impermeable layer, right? Above the groundwater table, if you have an impermeable layer like this, above the groundwater table, if you have impermeable layer like this, above the groundwater table, if you have impermeable layer like this, which contains a saturated soil mass, from where sufficient quantity of discharge can be extracted. Above the groundwater table, if you have an impermeable layer which contains a saturated soil mass from where sufficient quantity of discharge can be extracted, that is known as purged aquifer. So this is my impermeable layer. And this is my saturated soil mass. This is my saturated soil mass, right? So how we define the purged aquifer? Purged aquifer is defined as above the groundwater table, if any impermeable layer is present which contains sufficient quantity of saturated soil mass from where sufficient quantity of water can be extracted, that is termed as the purged aquifer. So these are the three different varieties of aquifers that are present: unconfined aquifer, confined aquifer, and last one is the purged aquifer. So basically, if I just summarize all the things, extraction of groundwater depends upon two factors. First one is the porosity, second one is the permeability. Extraction of groundwater only happens through zone of saturation, that is the groundwater table zone. Porosity for fine-grained soil is more and permeability for coarse-grained soil is more. Permeability is directly related with the surface area of the soil medium. If surface area is more surface area will offer more frictional resistance, and due to more frictional resistance, the flow of water inside the interconnecting voids of the soil medium, it will be hindered more. So permeability of the soil medium will be less. Then we have talked about specific yield and specific retention. So if flow is taking place under the action of gravity, the total quantity of water which will flow out is defined using specific yield, which is equal to volume of water drained divided by the total volume of medium drained. And specific retention basically tells us about how much quantity of water is retained against the action of gravity. One more thing, when we talk about the flow of water inside the soil medium, this flow will take place under the action of seepage velocity. Means seepage velocity is the actual velocity of flow. Okay. And then we have seen different geological formations in which aquifer has the largest size of the particle, then you have acutard, then you have aciclude. Based on this, we have defined the relation of porosity and permeability for these geological formations. So I hope you have found this session pretty much useful with respect to your technical exam. We at IMS GATE Academy offer you with 3 types of courses. We offer you with online program, we offer you offline program, and we also offer you hybrid program. You just check into our website imsindia.com. There you will find one feature of zero fee program. You can just register yourself for this zero fee program, and without charging even a single penny, we give you huge amount of lectures and some amount of content also. So this is all from my side for this session. Join me tomorrow at same time 6 p.m. onwards, and we will come up with a very interesting topic of well hydraulics, that is extraction of this groundwater. I'll see you tomorrow. Have a great night ahead. Thank you so much. This is Prateek Mishra signing off from the YouTube platform of IMS GATE Academy. Good night.